In this video, I'm going to describe three different applications of resistors: wires, heaters, and lights. The main function of a wire is to get energy from a source to a load. In most cases, the goal of the wire is to have as little resistance as possible. That is, it is a perfect conductor with resistance R equals 0 ohms. What happens in practice, though, is that wires are not ideal conductors. Let's start with one of the biggest wires, aluminum conductor steel reinforced cable. These wires have the biggest diameter and thus the lowest resistance. The goal of manufacturing and connecting these huge wires is, of course, to have the minimum resistance possible, but you probably won't find their properties described in ohms or ohms per mile. Rather, you'll find it described in percent of lost power per mile or per 100 miles. For instance, if 1,000 watts are generated at the generating station and 990 watts are consumed in the houses and businesses, then 10 watts were dissipated along the way, and you would say the power losses due to transmission were 1%. In our typical circuit diagram, we don't worry about the power dissipated in the wires. Rather, we assume that the wires are perfect conductors. For instance, if we hooked up a 12-volt battery to two resistors, as in this diagram, we'd assume that both resistors had a high end of 12 volts. That assumption would probably be perfectly valid if R1 and R2 were really high resistances. The resistance of the wires would be negligible and they wouldn't be likely to heat up, and they would have the same voltage here and here. But if the resistance of the loads were very small, for instance 1 ohm, then they might be on the same order as the resistance in the wires. The voltage here would be less than 12 volts, and the voltage here would be lower still. In any case, the ideal wire that we tend to use in our circuit analysis is R equals 0. That is, we treat the wire as a perfect conductor, and the voltage throughout that wire is the same. For a real wire, it's generally sufficient that the resistance of the wire is much, much less than the resistance of the load. This makes the circuit behave almost identically to the ideal case. What's bad, though, is that if you have your real wire and your real load both have resistances near zero, what will happen then is that the current will flow very quickly through the circuit, generating lots of heat and possibly catching fire or exploding a battery. A lot of times, the thing at most risk of damage from the short circuit is the power source. Putting a circuit breaker or a fuse in series with the power source can prevent damage to the power source by shutting down the connection to the short circuit. This changes the resistance from 0 across the short to infinity across the break. Okay, let's move on to talk about space heaters as an application of resistors. This looks like the space heater that we had in our basement bathroom several years ago. Now, I don't remember exactly what wattage it was, but let's say it was 1500 watts. The space heater was plugged into a 120 volt alternating current outlet. We'll find that with those two numbers and the correct equations, we can quickly find the electrical resistance R of the space heater and the electrical current I of the coming through when it is turned all the way up. The equation has basically three forms. Power equals IV, current times velocity. Power equals V squared over R, voltage squared over resistance. And P equals I squared R, power equals current squared times resistance. Of course, since all of them are equal to power, we can string them all together into one big equality. To find the resistance, note that the three variables of interest are power, voltage, and resistance. So we'll use P equals V squared over R. So that gets rearranged to solve for R equals V squared over P. We plug in 120 volts and 1500 watts. to find that our 1500 watt space heater has an effective resistance of 9.6 ohms when it's running full blast. You will also find that this draws 12.5 amps of current from the wall socket. Just to mention this, the wall socket image that I showed is rated for 15 amps and is designed to cut off the electricity in a fraction of a second if it goes over that 15 amps. Now let's get into light bulbs. For most of my life, light bulbs have come in this form. They had a socket that plugged into the electrical outlet, then the current flowed through this tungsten filament and got really bright and hot. If you touched a 60-watt bulb after it had been on for a few minutes, it would burn your hand. That's because it gave off just as much or more energy as radiant heat as visible light. Also, when I went to school, there were panels in the ceiling containing long fluorescent tube lights. These lights were more efficient in energy production, but they tended to have a hum, and they took a long time to warm up, and they often flickered. New advances in light bulbs are the CFL, or compact fluorescent light, and the LED, or light emitting diode light. Now, all three of these lights are designed to work with 120 volts alternating current, but you see one is 60 watts, one is 13 watts, and one is 8 watts. From that, we can calculate the resistance of these bulbs to be 1100 ohms, 1800 ohms, and 240 ohms. And the current that runs through these bulbs is 0.1 amps, 0.07 amps, and 0.5 amps. So the ideal light bulb is the one who has the highest resistance and the lowest current, but still gives you the light you need to see. Sometimes, instead of giving a wattage and a voltage, light bulbs might be rated in a voltage and a current. You can still find the resistance of this bulb from resistance equals voltage divided by current. This is a very small resistance compared to the household bulbs we were just looking at. And compared to the 60 watt tungsten filament bulb we were looking at earlier, this 0.75 watt filament bulb seems quite negligible. Even so, you can sometimes use a very low wattage to produce a small area of useful light in front of you by using parabolic mirrors to focus all of the light in one direction. I think that sums up most of what I wanted to say about applications of resistors. Let me show you a couple of little tricks about algebra before I go. It's something you can do whenever you have equations where one variable is a product of the other two. In these cases, remember that the voltage across a resistor is equal to the current through it times its resistance, and the power dissipated across a resistor is the current through it times the voltage across it. If I cover up the I in the little circle, the V is over the R, and if I cover up the R, the V is over the I. So that allowed me to quickly come up with the equations involving the quotients without thinking too much. You can see that the same thing happens with the power current voltage relationship. There could be quite a number of relationships that have this form. Here I have the definition of capacitance, the equation for the ideal gas law, and the equation for energy stored in a capacitor. So to sum up, this discussion has been about applications where the purpose of the resistor is to generate light and heat, or to get the current to something that produces light and heat without heating up much itself. I realize now that I've only talked about these resistors whose purpose is generating light or heat. Wikipedia describes the use of resistors to reduce current flow, adjust signal levels, to divide voltages, bias active elements, and terminate transmission lines. There's also a manually adjustable form of resistor called a potentiometer. Variable resistors can be used to adjust circuit elements such as a volume control or a lamp dimmer. There are also resistors that can be used as sensing devices for heat, light, humidity, force, or chemical activity. So I've just scratched the surface here in talking about lights and heaters and wires. Still, I hope it's been a good introduction. Thank you for watching.